Galvanic cell. Certain terms and vocabulary that you should be familiar with in this lesson. E0 cell is called the standard cell potential when the molar concentration of the reagent is 1 mole per liter and the temperature is 25 degrees Celsius. E cell. The notation is slightly different. The standard conditions are changed. And this is called the cell potential when the concentration of the cell is anything other than 1 mole per liter. We can refer it to as cell potential. SRP. SRP is called the standard reduction potential. These are the values that we will be using to determine cell potentials, and the values will be provided for you for performing the calculations. OHR is the acronym for oxidation half reaction. RHR represents the reduction half reaction. NCR is referred to as the net cell reaction. Formerly, it used to be called net ionic equation for single displacement reactions. NE is a term that we will have to calculate while we are balancing the reactions between the oxidation half reaction and reduction half reaction. When an equation is balanced, the number of electrons lost is equals to number of electrons gained, and Ne represents this number. These are certain questions that you may want to be able to answer by the end of this lesson. Why is the anode at a negative potential? What are the functions of a salt bridge? What is the difference between standard cell potential and cell potential? And how will you calculate cell potential? This is how a galvanic cell is represented. We refer to this cell as a galvanic cell when the electrodes used are zinc as the anode and copper as the cathode. I have placed the zinc electrode in the left compartment in a 1 molar solution of zinc sulfate, and I have placed copper in the right compartment with a 1 molar solution of copper sulfate. We talked about standard reduction potential values. Zinc and copper has standard reduction potential values. The values are given as minus 0.76 is the standard reduction potential value for zinc, and positive 0.34 volt is the standard reduction potential for copper. These values are given to you on a table, or the numerical values will be provided for you during a calculation. Now, by looking at these values, we can determine which electrode will undergo oxidation and which electrode will undergo reduction. The standard reduction potential values, since the name says reduction potential values, the larger the standard reduction potential value, greater is its tendency to undergo reduction. So in this case, copper has got a larger value, 0.34 volt, whereas zinc is minus 0.76 volt is a lower value. Therefore, copper has a greater tendency to undergo reduction in comparison to zinc. Therefore, we can use this information and calculate what we refer to as a standard cell potential using this equation. E0 cell is equals to E0 cathode minus E0 anode, or E0 cell is equal to 0.34 minus 0.76 gives you 1.10 as a cell potential. So if you set up an electrochemical cell, or in this case galvanic cell, with zinc as the anode and copper as the cathode, and the molar concentrations are 1m and 1m for both the solutions, the standard cell potential that we should be able to read in the voltmeter is 1.10 volt, and you can theoretically calculate it using the standard reduction potential values. The next thing that we are going to look at is what happens at the anode and what happens at the cathode, or how do we determine which electrode is the anode and which electrode is the cathode. the electrode at which oxidation takes place, we refer it to as an anode. So in this case, zinc undergoes oxidation. Therefore, zinc electrode is the anode. Copper undergoes reduction. Therefore, copper is the cathode. Since the reaction at the anode is oxidation, we can write the reaction as Zn changing to Zn2 plus 2 electrons. What we see happening in the left compartment or the anodic compartment is the metallic zinc dissolves, changes into Zn2 plus, and it produces electrons. The electrons tend to reside on the electrode, and the solution becomes rich in zinc ions. And on the right compartment where there is reduction, here the copper ions gains electrons and changes into copper. That's what happens here, which means the copper ions in solution needs electrons. They take it from the metal, and when that happens, the metal becomes positively charged, and thereby the cathode will be at a positive potential and anode will be at a negative potential because of oxidation in the anodic compartment and reduction in the cathodic compartment. So what we have ideally created here is a potential difference. The cathode, because it's losing all the electrons for the process of reduction to take place, is deficient in electrons, or we can say it's at a low potential. The anode, or zinc, because it is undergoing oxidation, is producing electrons, is rich in electrons. It's high potential. So if you actually connect the two electrodes, the electrons start flowing from one to the other, and it generates an electrical current when electrons flow through an external circuit. And the potential difference is 1.10 volt. That's what really happens here. So we can explain why there is a potential difference, and we can calculate the cell potential by explaining the chemistry behind the reactions, that is the oxidation half reaction on the left compartment and reduction half reaction on the right compartment. Now, one of the problems that would happen is with time, the concentration of zinc ions increases, making this container positively charged and making the right compartment, because the copper is going to be reduced, gains electrons, and it changes into solid copper. And therefore what happens is the concentration of copper ions decreases, and therefore the solution becomes negatively charged. There is a decrease in positive ions in the aqueous solution. The copper ions are coming from copper sulfate that was dissolved in it. The ratio of copper 2 plus to SO4 2 minus is not maintained anymore. The copper ions are reduced, they change into solid. Therefore, the sulfate ions still remain in the solution. So the solution is negatively charged due to the excess of sulfate ions. And how do we actually neutralize the solution or make the solution electrically neutral? We add what we refer to as a salt bridge to this device. A salt bridge contains a glass tube, contains agar, in which sodium nitrate or potassium nitrate or any salts containing only spectator ions are present. So in this case, we have potassium nitrate. So we have K positive and NO3 minus. When the cathodic compartment becomes rich in electrons, in order to maintain electrical neutrality, what happens is you'll have the positive ions or potassium ions actually move into the solution. And in the anodic compartment, because we have more of the zinc ions is becoming positively charged, the nitrate ions, which are negatively charged, starts moving into that. So what happens is the salt bridge can maintain the electrical neutrality of the solution by allowing the positive and negative ions to migrate into the anodic and cathodic compartments. So the anode compartment will remain electrically neutral by the nitrate ions migrating into it, and the cathodic compartment will become electrically neutral by the potassium ions migrating into it. one of the important functions of the salt bridge is to maintain electrical neutrality, and this will help in completing the cell circuit. If the salt bridge is not there, what normally would happen is the current will flow for a very short time and then it'll stop flowing. But if you have a salt bridge, there will be a steady flow of current, and this value will be 1.10 as long as the concentration remains the same. So the function of the salt bridge is to complete the cell circuit. So two functions: one, to complete the cell circuit, and two, to maintain electrical neutrality. You are also expected to write the reactions, the oxidation half reaction, the reduction half reaction, and add them up and write the net cell reaction. This is an expectation. So you will be expected to draw the electrochemical cell, label it as anode, cathode, or determine the electrode that would be the anode and the cathode. Write the chemical reaction that takes place at the anode, which is oxidation, and the oxidation half reaction. It's called the half reaction because that's the reaction taking place in the left side of the compartment of the galvanic cell. The oxidation half reaction takes place in the left compartment here, and the reduction half reaction takes place in the right compartment here. So we have separated the reactions as two, that is oxidation half reaction and reduction half reaction. So this is the oxidation half reaction. So the oxidation half reaction is a reaction taking place in the anodic compartment. Zinc changes into Zn2 plus 2 electrons, and the reduction half reaction is the reaction taking place in the right compartment, Cu2 positive plus 2 electrons, giving you Cu. Here the number of electrons lost in the first reaction is equal to the number of electrons needed in the second reaction. So they are equal, or we can say the equation is balanced. Now we add the two equations, cancel out the common terms, which is the 2 electrons, and that is also referred to as Ne, number of moles of electrons transferred in the balanced equation. So the net cell reaction would be a net ionic equation for the single displacement reaction that you've seen. Zn plus Cu2 positive gives you Zn2 positive plus Cu. So we have seen how we can calculate standard cell potential, E0 cathode minus E0 anode, and the value is 1.10 volt. The value is also positive, which means the cell potential or the voltage can be used for doing work. If on calculating the standard cell potential you get a negative value, the reactions that are taking place at the respective electrodes are incorrect. If I choose copper as anode and zinc as cathode, then the standard cell potential would have been minus 1.10, which means the choice of electrodes that I have made is incorrect, especially while representing a galvanic cell or electrochemical cell as represented here. Now all the time it's not possible to draw these diagrams, so we also use what we refer to as a cell notation. So the cell notation is written beneath the diagram here. Zn solid separated by Zn2 plus, and in brackets I include the concentration. In this case it is 1m. The double lines or the two lines represent the salt bridge, followed by the reaction that is taking place in the right compartment, which is the cathodic compartment. It's a reduction, Cu2 positive, and it's an aqueous solution. The concentration is 1m, changing to Cu. So we can actually use that. So zinc gets oxidized and copper gets reduced. So instead of drawing the diagram, we can use the cell notation to represent an electrochemical cell. So the expectation at this point of time, you should be able to draw an electrochemical cell, identify the anode, identify the cathode, calculate the cell potential or standard cell potential, write the oxidation half reaction, write the reduction half reaction, add the two equations, write the net cell reaction, calculate the number of electrons lost and gained, which should be equal, and we represent it as Ne. And we should also be able to make a cell notation as shown here. These are the expectations for writing an electrochemical cell, drawing it and explaining it. Now, if the concentrations change, then we will use a different method for calculating the cell potential. Then we do not call it standard cell potential. We call it cell potential when the concentrations do change, which also implies with time, since the concentrations of the zinc ions and copper ions in a galvanic cell changes, the EMF of the cell will also change. So the EMF of a cell depends on the concentration of the anodic compartment solution and the concentration of the cathodic compartment solution. And all of these changes have to take place at 25 degrees Celsius.